All right, so for the first part of our lesson here, we actually need to make a correction. This is 15.3 through 15.5. We're going to cover a few different sections today because they're all really closely related. We're talking about taking these functions and actually graphing them on a graph. So remember from our geometric sequences, one thing that you need to know, this is a big thing, is that geometric and exponential are, those two terms go hand in hand. They mean the same thing. So the same way that linear, we used to say that linear and arithmetic were the same, arithmetic. Now we want to say that geometric, and I have this written backwards, and exponential are going to be the same. And that's because, remember, the x itself is an exponent. That's why they call it that. So if I zoom in real quick on this example, I want you to notice some things about the graph, or about these problems, rather. All of these first numbers, remember, are the starting points. And because my exponent is just x, the starting point, that means they're telling me to use, is 0. So if I'm trying to match these graphs, and see, the first one says it has a starting point. Like when I read this equation, I read a starting point of 3 and a pattern multiplying by 2, which means it's going to be getting bigger and bigger. And if I look at the graphs, the only one that appears to be starting at 3 and getting bigger, take a second to look for yourself. Hopefully you match that with A starting point on the 0 line, which is the y-axis, of 3, and then it's increasing because it's multiplying by 2 every time. All right, my second equation is starting at a half, so it's starting at a lower value, but it's still increasing by 2 every time. All right, that looks like, to me, it's going to be C here, starting at a half, but it's still increasing. All right, now question 3, I'm starting at 3, but notice my fraction this time. This time, I'm multiplying by a half, or, remember, multiply by half is the same thing as divide by 2, which means now my graph needs to be getting smaller as I move forward. So I'm still going to be starting at 3, which that's B right here. But notice that when I go forward now, my graph is decreasing in size because I'm dividing or cutting it in half over and over again. So that means question 3 matches this graph B. So that leads us, obviously, by process of elimination, to say that question 4 goes with D. But let's look at why. Notice that the starting point here is -3. So we're now starting at a negative value, but I'm still multiplying. So this is a little weird because it's getting bigger even though it's getting smaller. Man, negatives make things really complicated. Just notice how even though it's growing in the negative direction, it's still growing very quickly. Another way you can think about this negative, try to compare A and D right here. I hope you see that they're very much the same graph, except the only thing is that D has been flipped, or notice that it's been reflected, right? That's what the negative value does, is it reflects. So let's look at how to actually graph some of these on our own. Okay, so we've just got 2 examples. Here is example 1. They're going to ask us to graph this without a calculator using the domain that they give us. So remember, domain, those are my x values. And really, that is just going to tell me my terms. So I'm going to take a second and kind of make a table. This is very similar to what we did today. So my table is, I've got -1, 0, 1, 2, 3, and 4. And if you remember, my function rule here actually tells me the starting point and the pattern. So remember, this number is my start, and the 1/2 is the pattern. That means my starting point is at 3, and mathematicians are weird, remember, they start at the 0 term, so my 0 term is 3, and my pattern is 1/2. So since my pattern is 1/2, that means I'm going to be dividing, that's the same as divide by 2. All right, so I'm going to divide these by 2. Well, if I divide 3 by 2, that gives me 3 over 2. And if I divide that by 2, I get 3 over 4 and 3 over 8 and 3 over 16. Notice how the bottom number is just multiplying by 2 every time since it's 1/2. And then if going forward is divide by 2, then going backwards must be multiply by 2, which means my first point there is going to be 6. And to be able to graph that, we literally just take the points that they give us and put them on the graph. So -1 is at 6, 0 is at 3, and then 1 is at, so half of that, 3 over 2, we're just cutting that in half, that's like 1.5, and then half of that, and then half of that. So you should notice we're getting really, really small here, and we're not going to connect them because they give us separate points. So do not connect. And remember, we call this discrete when they're not connected. Discrete. We haven't talked about that word in a while. All right, if you have questions, I want you to write your questions in your notes for this example so we can talk about that specifically tomorrow. All right, this question is very similar, except this time they don't give us a domain. So if they don't give us a domain, we're going to use a domain of all real numbers, which means we are going to need to connect our points in the end. So if we want to connect them, that means we're going to have a continuous graph. Continuous, connected. All right, so we're going to kind of start the same way by making a table, and then we'll just connect our values in the end. And I'll start with 0. Well, actually, I'll put 0 in the middle of our table. So let's do -2, -1, 0, 1, 2, 3. So remember, mathematicians start with 0, and our starting point is this 3. So start as 3. And then 4 is our pattern. That means I need to be multiplying by 4. So if I multiply by 4, I get 12 and 48 and 192. And then when I go backwards, remember, to go backwards, we've got to do the opposite. So to go backwards, I'm going to have to divide by 4. And since that doesn't divide well, I'll just write it as a fraction, 3 over 4. And if I do that one more time, I get 3 over 16. Now, if you need help with those fractions, put a little star in your notes that says you need help with the fractions. Okay, so my starting point here, remember my starting point, 0, is going to be at 3. Ooh, they don't make that easy to graph. And then at 1, we're going to be at 12. And at 2, we're going to be at 48. Oh, so this gets big really, really quickly. Okay. And then I can't even fit 192 on the graph. And if we go backwards one, remember, it's still just going to get really, really small. This time we want to connect because they don't give us a domain. So we're going to do all of this. So I'm connecting there. Okay, so now the only thing we have left to talk about is our range. And range is kind of a little bit weird here. So think about the y part of our table. If I keep going in this positive direction and multiplying, notice that it's just going to get bigger forever. So that's going to end up going to what we call positive infinity. We haven't really talked about how to write that yet, but I just want you to think that's going to continue to get larger and larger forever. If I go in the negative direction, I'm going to get smaller and smaller forever, but I'm not actually going to ever get into negative numbers. Notice my fractions are just going to get like a smaller and smaller piece, but I'm never going to get to 0, and especially not into the negative numbers. So I want to talk about how we write that. A few things. First of all, we said it's not ever going to get to 0. So there's a new word, and it's called an asymptote. asymptote. It's a funny word, asymptote. And what it means is that this function down here in this bottom corner is not ever going to reach 0. We're going to get really, really close, but technically, if we keep dividing by 4, we're just going to get smaller and smaller fractions or smaller and smaller decimals. So there is actually an asymptote right here, and we're saying that the y value is never going to reach 0. So there's an asymptote at y equals 0. So when we talk about the range then, my range values are y greater than or equal to 0. And it's greater than because all of the y values, you can look at the table or at the graph and notice that I'm always in the positive part for the y. It's going to go up forever, so that's why I'm saying greater than or equal to. And 0 is kind of this breaking point. And I'm going to show you one more that looks just a little bit different, and we'll see like when the range starts to look a little different than this specific problem. All right, so here's our last example, and I'm trying to show you two different things in this example. And just one more example of range, and then also an example with some transformations. So what we have graphed here, if you look, is the equation -2 times 3 to the x. So they already, if you kind of look here at the ordered pairs, they already give us some points. So I just want to show you the points in the table. So we have a 0, -2, and you could have figured this out on your own, right? Multiplying by 3, so we get -6. 2 gives me -18, and then if I go backwards, I can divide by 3, so -1 becomes -2/3, and I'll do another one just for good measure, -2/9. All right, so remember, that's because pattern forward is multiply by 3, backwards is divide by 3. Now, if I go ahead and name the domain and range, because all of this is connected, I know my domain's going to be all real numbers. And then range, remember what we just talked about. My fractions are going to keep approaching this 0 line, but this time, notice that my table is not going positive infinity forever. My table is going to go to negative infinity forever. See how it's going down forever on this right-hand side? One side is trying to get to 0, and the other side is trying to go down forever, which means my range is now going to be y is less than or equal to 0. So the greater than or less than symbol we can pull from if our starting point or if the points in our table in general are going to be positive or negative. And then let's talk about how we get this 0 point. So if I do this other function, g of x, notice that g of x is very much the same thing. It's very, very similar, except the only difference is it's got this +6, which means I can take the values that they've given me in my original table and just add 6 to each of them. So my 0 starting point is now going to be at, let's see, that's going to be 4. I did -2 plus 6. My 1 point is now going to be at 0. My 2 point is now going to be at -12. And if I go, I'll only go backwards 1 since that's going to get difficult. -2/3 plus 6 is going to be 5 1/3. And I lied, I'll actually go back one more. So if I do one more, that's going to be -2, 5, and let's see, 7/9. All right, so I'm going to pause the video and go ahead and graph those so we can see how is this function going to compare to the one we had before. All right, so if you notice now, all my points are just a little bit higher than they were before. And what you all have learned is that this +6, think about it, that's outside the parentheses. It's not with the variable x. So this +6 is doing what you assume that it would do, and it's moving or shifting my graph. So we'll say it's going to shift my graph up 6. Now notice that that means that my y values are still going to go negative forever. However, this time my function is not going to be approaching the 0 line, but think about these fractions that I have at the end here, these 5s. It's now going to be approaching 6 line. So I haven't drawn that very well because it looks like I've crossed it. But if I write my domain and range now, my domain is still all real numbers, but now my range is y less than or equal to 6. So notice that similar to what we had with the absolute value, the range, the value itself is coming from the number on the outside. So the reason that all these other ranges had to do with 0 was because we weren't adding or subtracting anything. If you add something, that's going to change where, remember that line is called an asymptote, it's going to change where your asymptote value is. So keep these notes for domain and range, and then we'll keep working on this in class tomorrow.